This is architecture very based on size, based on that we can classify the memory hierarchy. There are different kinds of memories like registers, then cache memory, main memory, and secondary memory. Here, the size of the register is very less, but speed is high, and cost is also high. Okay, the cache memory is kept in between the processor and the main memory. Here, the cost of this cache memory is high when compared to this secondary cache and main memory, but less than registers. Okay, we can have two different kinds of cache memory, maybe L1 cache or L2 cache. It's for increasing the speed of the computation. And third one is about main memory. It's a volatile memory. Whatever program you have to execute, that is going to be loaded to the main memory. Then magnetic disk or secondary memory. It's a non-volatile memory, hard disk. The data is stored in the secondary memory. So these are various types of memory we have. This can be classified based on the size, speed, and cost. The first one is about cache memory. It's for increase the speed of the computation. We are using this cache memory. It is being kept in between the processor and the main memory. Here, this cache memory can be loaded with that blocks of data based on this scheme called locality of reference. What do you mean locality of reference? This may be a temporal or spatial locality of reference. What do you mean by temporal? Temporal in the sense the recently executed instruction may be used again, so that is going to be loaded in this cache memory. And spatial locality of reference, the instruction which you are currently using, then immediate may be used again. Okay, so this close to that recent instruction will be loaded to that memory. It's called spatial locality of reference. So locality of reference is nothing but the areas of a program are executed repeatedly during some period of time. Then cache memory, it's kept in between the processor and the main memory. Here, how do you find if processor needs some data or instruction? First, that will be searched in the cache memory. It's called cache hit. It's not available. Then it will be searched in the main memory. Actually, time taken to access data from cache is very less when compared to that time taken to access data from the main memory. The speed of the processor is high when compared to memory system. So to cope up with that speed, we are going to have this cache memory in between the processor and the main memory. Here, what are things are going to be loaded into the cache memory? Okay, we can go for using this mapping function. And if the cache memory is full, then we have to replace some blocks of from this cache. That can be done using the replacement algorithms. Then whatever things you are searching in the cache memory, it's available. Then you can say it's a read hit. The hit in the sense the required data is available in that cache memory. So in order to go to the main memory, you can access in the cache itself. Then you want to write something into that cache memory that will be reflected later in the main memory. So it's called write hit. The particular block is available, then only you can write the data into that cache memory. So if the block is available in that cache, then we can say its block is available, we can write it. It's called write hit. Here once the data has been written in the cache memory, it is reflected immediately in the simultaneously is called write through protocol. Whatever you are writing in the cache memory, the same thing is also reflected in that main memory is called write through protocol. Then write back protocol, copy back protocol is nothing but you are first updating the cache memory. Once it is going to be replaced, it's been removed from the cache, that time it's going to be update the content in the main memory. This is called write back or copy back protocol. Then here we have a bit called dirty or modified bit. It's going to say whether the cache, the block available in the cache is modified or it's not modified. Okay, once you are reading data from the main memory, it's been in the cache memory, it's not yet modified with any instruction, then it's not a modified, the modified bit may be 0 or it's been updated. Then It's having some day, it's been set with 1. Then whenever the block is going to be replaced from the cache, that time the modified bit is verified. If 0 means okay, no need to replace because both blocks are same. The cache memory and this main memory, the blocks are same. Then if it has been modified, then you have to replace that content in that main memory. This purpose we have this dirty modified bit in cache. Cache miss the sense here we are trying to read the particular block in the cache memory, it's not available. Then what happened? The read miss occurs. Then the process trying to write something into that cache, the particular block is not available, it's called write miss. Then how do you go for accessing data from the cache memory? Here we have mapping functions determine how memory blocks are placed in that cache. For example, here the cache is having a 128 blocks of 16 words each. Then the total size of the cache is 2k words. The main memory is 16-bit address. Then it can have capacity of 64k words. And it's having 4000 blocks of 16 words each. So here we have this 2k words. Here we have the 4k blocks. There are 3 types of mapping function. How do you place that main memory content to that cache memory? That can be done using this direct mapping, associate mapping, set associate mapping. The direct mapping here, this is a diagram. Assume this is a cache memory, you have 128 blocks. Each blocks we have a 16-bit word. Here the main memory capacity is around 4k blocks. Here the main memory address we have 16-bit. In this diagram we have 16-bit, 5 bits for tag and 7 for block and 4 for words. In this case I want to place 127 into this cache memory, then I can go for this operation of 127 modulo 127, that results 0. It will be placed in that 0 block. Okay, if I have 128, then I have to apply this 128 modulo 127, that results 1. So this 128 will be placed in this block 1. This is the way we are going to place the content or the block into this cache memory. This is called mapping function. The direct mapping use this formula of the block number of main memory modulo the block number of this cache memory. Okay. So here the first 4 words. The word is represented using 4 bits. So we have only 16 words in this block. It's going to represent that 4 bit for 16 words in a block. Okay. Then here the 7 for identifying one particular block. We have 128, so we have 7. Then this tag for setting whether what are the caches, what are the blocks are available or it's been occupied, that can be represented using a tag 5 bits. So this is the way we can do it in this direct mapping. The drawbacks are sometimes keep on we are using one particular block, the remaining blocks are not occupied. We are wasting that memory. So to avoid this we can go for associate mapping. The associate mapping, here we have the address like the 16 bits, we have 12 for tag and 4 for words. Here wherever the free space is available you can place it here. Okay, then the set associative is a combination of this both direct and associate mapping. In this case, here we have main memory, the same 4K. Here we have 128 blocks of cache memory. Here we are going to take 2 blocks as a one set of memory. Here block 0 and 1 is our set 0 and 2 and 3 is a set 1. Inside the set we can place anywhere. This is associate mapping. But how do you find the particular set? That will be identified using that formula. This block number by this memory block number by cache memory block number, we have around 64. Okay, then after applying this modulo operation, the particular set will be identified. In that set we can use this block 0 or 1. For example, I'm to apply, you want to place this 64, the block 64 in this cache memory. Apply 64 by 63 Here we'll get this 1. So we can place the 64 in set 1. The set 1 where will we keep either 2 or 3. Here the main memory address will be like word for finding particular word in the block 4 bits. We have 64 set represented using the 6 bits and tag 6 bits. This way we can map the blocks into this main memory blocks into this cache memory. The performance considerations here, it's to achieve the possible performance at low cost. Okay, so how do you go for increase the fast or the speed of the computation? You can go for this interleaving method. They divide the memory system into number of memory modules. Okay, each module is having this address buffer register or data buffer register. Then the interleaving concept here we have two types in this. The module 1 address in the module. Here the consecutive information, the words can be placed in one particular module, then other maybe in the second module, third module. You want to get one particular set of words, then you can go for finding this module 1, get this data. And here in this case the consecutive will be stored in that consecutive modules. So here each one will be, so if in this case you have to access one particular word, then where and all you have this instruction, that modules will be busy. Here it will be in the consecutive instruction will be one particular module, only that will be busy. Then virtual memory system. In this virtual memory system, here it's for increasing the effective size of the memory system, where we cannot load that program in this main memory. When main memory is less when compared to the program size, there you can go for this virtual memory concept. So cache memory is for increase the speed of this computation, and virtual memory for effective size of the memory system. Here the physical memory is not that much large for holding entire program. That time we can go for this virtual memory concept. Here only the required portion of the program is loaded into that main memory, remaining will be in that secondary memory. So whenever the program is needed, that is going to be loaded into that virtual memory. Clear. The operating system is automatically transfer the data between the main memory and secondary memory. Here we have a MMU, the memory management unit, for calculating this virtual address into that physical address. So here the term is called virtual or the logical address. Okay. Here the processor issues binary address. Okay. This is called virtual or logical address. The memory management unit will convert this virtual address into that physical address to get the particular portion of this program. So here we have this memory management unit that converts the virtual address into physical address. Okay, we'll see how do you convert this one. So this is called address translation. Here we have a set of units called pages. The pages consist of block of words, and it occupies the continuous locations. Here the page is a basic unit information that is transferred between secondary storage and the main storage. You can have the one page of information from the secondary to that main memory. The size of page can be from 2K to 16K bytes. The pages should not be too small because it will take more access, or it should not be too large because that cannot be occupied much. So here the concept of virtual memory are similar to the concept of cache memory. Here we have this, it's for bridging the gap between the processor and the main memory, but virtual memory is for bringing that gap between the main memory and secondary memory. How do you go for this address translation, this logical address into that physical address? You can have this table called page table, then main memory address where it is stored in that page, the current status of the page which is available currently in that main memory. Okay, the main memory page we can say it's a frame. We have a base register, it's having the starting address of the page table, it's called page table base register. Then the virtual page number generated by the processor is added to the content in the page table register. For example, see, this is the page table base register, it's having the starting address of the page table. This is the virtual address we want to translate into that physical address. So here the offset will be the same offset will be there. Okay, but how do you convert this virtual page number into physical address? That will be done using this calculation. This page table address, the starting address of this page table will be given here. Then virtual page number will be added with that page table address. Then you can get the particular location. There you have the address of that particular block. Then that will be taken page frame. This will be the physical address. This way you can translate logical address into that physical address. Sometimes it takes hectic. We cannot have all this entire page table into that processor chip or in the cache memory. So we can divide this complexity with TLB method. This translation look-aside buffer that holds the page table entries of most recently used. Okay, the TLB is having the same way, but before we are going to this page register, page table base register, we can check with that TLB translation look-aside buffer. It's having the content of most recently used pages. Then it's not available, you can go to this page table base register. Otherwise, you can get here itself. It's called hit. So page number will be verified whether the particular page is available here. Yes, it's available means it occurs. Get that corresponding page memory. Then add with the offset, you can get this main memory address. This way you can use this virtual memory technique. Next topic is about input-output organizations, data transfer techniques. Here we have different units like input unit, output unit, and it's also called peripherals. How do you use this? How do you transfer data between memory and this IO unit? Here we need this CPU. With CPU control, we are going to transfer data from input unit to the memory unit or memory unit to the output unit. To avoid this one, to increase the speed, you can go for having the direct communications. It's called IO organization or data transfer techniques. Okay, the peripheral device, that the input output devices, it's called peripherals. Here, how do you transfer data directly to that IO devices into the IO devices to the memory. Okay, so with intervention of this CPU, we can do it. Otherwise, you can go for these methods like programmed IO, interrupt initiated IO, direct memory access. The programmed IO instructions are the result of IO instructions written in the computer program. You have to execute the corresponding instruction for transfer. Then you can go for using some interrupts for initiating this IO transfer. Or you can go for this direct memory access. Okay, without the intervention of the CPU, you can go for transferring data to that memory to the IO or IO to the memory. So data out register, data in register, address registers, control signal will be generated. Then DMA request will be given, address will be loaded, address lines, and the data will be fetched. Then you can go for this IOP, input-output processor. It's a processor with direct memory access capability. It's divided into that memory and number of processors that controls and manages the IO task. It's similar to the CPU. Okay, so if you're going to do this direct memory access, we need something like a CPU. We can use this IOP. So that transfer data between the peripherals to the memory. So time will be reduced here to improve the performance of the computation. That's why we have to go for this IOP. So here there's a memory unit, we have a CPU and the IOP. Here peripheral devices 1, 2, 3 we have. In this case memory, all these are connected using a bus. So here without IOP, the devices they have to communicate with the CPU. Then it has to communicate with the memory unit, and if it is free, it's not busy, then it has to say I'm free, you can transfer, then giving information back to this one, then transfer is taken like this. But in direct memory access, here we can go for sending information directly to this IOP and devices to IOP. This way you can transfer the data. Okay. So need for input-output processor. The input-output interface provides the method for transferring the information between the internal storage and the external IO devices. The peripherals connected to the computer need special communication links for interfacing them with central processing unit. So the purpose of communication link is to resolve differences that exist between the central computer and each peripheral devices. So differences are the peripherals are electromagnetically and electromagnetic devices. The data transfer of peripherals is usually slower than the transfer rate of CPU, and consequently Synchronization mechanism may be needed here. Then the operating modes of peripherals are different from each other and must be controlled not to disturb the operation of the peripherals connected to the CPU.